many weeks, 3 weeks of Easter break? Actually, the way it starts very, very good. 3 weeks Easter break before exam. 3 weeks Easter break, 1 week revision, then your exam. Very nice, nicely arranged. Very good. Other OUs, other universities, not Easter break and after, and 8 more weeks of lectures after revision and exam. Okay, if you look at other overseas university partners that I think that so you all should be able to do well. Okay. The 2 exam papers, I mean, you can also get all the past exam papers from NT Library. That's what I understand. But pass to you 2 papers, and last year's paper, April 1 and August. Okay, the main paper and the receipt paper. So what we're trying to do today is we just want to go through the questions in those 2 papers. Now you notice some of the past, tutorial questions in the past appear on past year papers. Do you notice that? The exam papers are not set by me, it's all set by Glasgow, so you have every right to do so. Okay, except the exam papers are similar to tutorial papers, except some numbers are changed. Okay? But of course, there are also new questions as well, new questions. Okay? So it's very important you must do all the tutorial questions, do all tutorial questions, attend every lecture, and you will do well, I hope. Okay, so you have 2 papers, last year's papers. Okay, so today, we'd like to go through because some of these exam questions are actually tutorial questions, we're covered on some of these questions are covered during our lecture tutorial session, lecture tutorial. Lectures that put into examples and they happen to be taken from past year examples. So we will not cover those. Okay, just change in numbers, I notice a change in numbers. So those that we have covered already, we will not cover it. Okay, we'll cover some new ones that we have not come across. Is that okay? No point that we cover in the lectures or tutorial, then go through it again in exactly no point. Unless you actually take some of the lectures. Okay, alright. I have before me here, question 1, this is a nothing more.
No answer. Oh, you do it, yeah.
This IT problem. Let's go over that. Oops.
Oh, it's too long. Gerald, you still remember all this? Sure. All this. And let's say I give you this. The bank again. All the way. Okay, yeah. After I study.
going on.
Why are you concerned about them? You call them. You're concerned about them, then you call them.
He's concerned of the girl.
Give me a moment. I'll scroll it up and down. I'll turn off and off.
Why you didn't call your mother? Why you didn't call your mother?
Okay, that's better. Okay, let's look at the April. This is August, April.
From now on, or from this
Okay, let's look at August, April first. Okay, question 1, August, April. 2014. Alright, this question 1, if you look at it, can you see? Okay, question 1, August 2014 paper. Okay, this question, if you look at it, looks familiar, isn't it? Does it look familiar? Where can you find it in your lecture slides? Slide number 1. Lecture slides? Well, let me pick up the lecture slides.
Can you use the video or I watch the YouTube, watch any tired. Crazy.
Every minute watch 1 hour
I give power reduction. The controls are.
Rewind, play. Rewind, play.
I also do that.
Okay. This is very similar to lecture slide 49. The lecture slide 49. Okay. Now, for this question here, there are 3 parts. Question 1, it says A is to give a quantitative definition for the viscosity of a fluid and explain some of the practical causes of viscosity in fluid motion. Okay, this part I will just briefly go through because it's descriptive. It tests your understanding of viscosity of a fluid. Okay? Then part B here, it says explain with an aid of graphical representation how Newtonian and non-Newtonian fluids are characterized by their shear stress versus shear rate relationships. Okay? That's part B. So B, I can also go through briefly so that you understand the style and how to actually answer a question like this, where it starts, where it ends. I also will answer. I write this sentence. Do I write some more? Do I write some more? And don't end to it. Then C here, part C, it says a 2-meter wide and 4-meter tall. Part C, is it a 2-meter wide and 4-meter tall? How come the screen here? Go further up. Anyway, that's why we should have, screen with a black margin or something all white in there. Oh, it's like that. Okay, the 2-meter wide and a 4-meter tall rectangle is 3 to 5.1. So it's very similar to this question. Okay, so it's been covered in the lecture, and therefore I will not cover part C. Okay? So that's why it's so very important to attend lectures and do all the tutorial questions. Okay, question 1. Question 1. Q1. This is the Yeah, I'm going to put one. August, 2040. Okay? Okay, question one. Give a quantitative definition for the viscosity of a fluid. Explain some of the principal causes of viscosity in fluid motion. So we know that viscosity is very important in fluid mechanics because the viscosity is very fundamental as the fundamental relationship viscosity with the velocity gradient. And this is fundamental and it gives rise to many other important equations or formulae in mechanics. So, how do we answer a question like that? Quantitative definition of viscosity. Quantitative, that means what? You have to give the relationship, okay? The formula that involves viscosity, the basic formula involving viscosity. So, and it also says, explain some of the practical causes of viscosity in fluid motion. So, it can be therefore answered this way. Okay, this is part A. Alright. You can say consider flat plate. Okay, consider flat plate. That's it. Alright. Show. Make it show below. Okay. And of course, you need to draw your flat plate. If you see. Okay. And of course, you can draw your exaggerated particle size, the velocity profile for flat plate. Smaller and smaller. Supposed to be a straight line. Supposed to be a straight line. Okay. And this is your y-axis. And this flat plate has area A. Okay. And this plate moves with a velocity capital U. And this is a viscous fluid. Okay. And of course, usually there's a force F to move the top plate. And you can say this is the plate separation distance H. And this is the fixed plate with, therefore, the velocity U is 0. If it's small u, there's a big U. Okay? And this is velocity profile. Okay, small u is the function of y. It's function of the distance towards the top plate. Okay. Okay. So we can therefore say that if, for example, if no pressure gradient, if no pressure gradient exists along the plate, in direction of motion, direction of motion, and it's not break yet, Not break yet, too early for break. and then the fluid has a linear velocity. Okay? Alright. So the linear velocity is by virtue of the top plate moving because of a force. This top plate, bottom plate is stiff, top plate moving. So you get a linear velocity profile. And this statement is important if no pressure gradient exists. In other words, the plates are there. So originally, the fluid is not flowing. Fluid is flowing because of a pressure gradient. So you think originally the fluid is not flowing. There's no pressure gradient. And because of a force pushing the top plate forward, so the top plate moves and it drags the fluid layers all the way so that you have a linear velocity profile. Okay, that's what it means here. Then, so if so must comma here. Okay. In this case, then what did Newton say? So Newton postulated, that means predicted or theoretical, or what is stated that shear force or shear stress, between two adjoining layers is proportional, not alpha, proportional to the rate of change of velocity. That is, then you must state the quantitative relationship. Okay, there's shear stress tau being a stress. Stress is actually a force over area. Okay, as we know, it's very basic. And this shear stress is actually proportional to the velocity gradient, del u, del y. Okay? And where does mu come from? There's a mu. Since tau is idea, since tau is proportional to del u, del y, the constant of proportionality is the viscosity mu. So tau is equal to mu del u, del y. Okay? This is the quantitative relationship. Right? Then we have to explain what mu is. Okay? Mu is what? Mu is dynamic viscosity. Sometimes it's called coefficient of viscosity. Okay? And tau is a stress, or we know that stress, and del u del y is the velocity gradient, and sometimes it's also called the shear strain rate. Shear strain rate. Okay? This is a gradient. Also called velocity gradient. Okay, so there is part A. Part A. Then part B, explain with an aid of graphical representation how Newtonian and non-Newtonian fluids are categorized by their shear stress versus shear rate relationship. Okay, so it says explain with an aid of graphical representation. That means you must show graphs, sketches. Okay? The examiner want to see you sketch some graph, some relationship. So don't miss it. Right? Because he allocates some marks for the graphs. So if the graphs are not there, you don't get those marks. right? So now, did I miss something? Here. For explain some of the practical causes, that's how the grammar structure before we go further to E. Okay, with that, the first part of part A, the second part of part A, explain some of the practical causes of viscosity. So some of the practical causes of viscosity. How do we explain? Now, if you have attended my lectures, just talking. You're okay? You're okay? Alright? The back is okay, but the front, not okay. You are asking a lot of questions. Actually, right? You asking your back question? No. Okay, right. So some physical causes. Okay, so how to explain viscosity? So you can say that viscosity, some physical causes. Can you see? So now remember this, all these graphs these sketches was in the notes. Okay, these are the fluid particles. And this one, the shear stress, because they actually rubbing against each other. So this fluid particle here will experience a shear force that goes in the direction that's forward because of this fluid particle here. And this fluid particle will experience equal and opposite shear force in the opposite direction. So likewise, this one, they are equal and opposite. Okay? And so on and so forth. So because of this friction, so actually it's because of it gives rise to a viscosity. Okay? So I just do a sketch here. There's one, and the second cause is actually momentum transfer. Okay, momentum transfer. Okay. Momentum transfer from one layer to another. Okay. From one layer to another. So you have this layer contains these fluid particles, in fact, down to atomic level in same molecules. And so this layer moves at certain velocity, and of course, because of turbulence and random motion, so it will transfer momentum from this layer to this layer, and the fluid particles from the bottom layer will also transfer momentum because they move across each other's layer. They either slow it down or speeding it up. Slow it down or speeding it up. And of course, you can write something with a little explanation of this. I just want to do a sketch. I don't write everything down. Okay? So, we have fluid particles in this layer, and fluid particles in this layer, and okay, this layer could be further from the wall. So it tends to transfer because this one eventually can actually move to this layer and vice versa, and therefore this one will go to try to speed up this layer, and the fluid particles from this layer come to this layer will try to slow it down. And so this creates viscosity. It makes the fluid viscous because of momentum transfer. So you all can write, explain. Okay, I write everything here. Alright, next is on the part B, on the Newtonian. Okay, B, sketch. Sketch is involved. So how do you actually explain that? Okay, so B, you have seen that graph that during my lecture on Newtonian and non-Newtonian fluid. Now, how is the relationship like between shear stress and the shear strain rate, Lu, Ly, for Newtonian fluid? For Newtonian fluid, anybody? Relationship between shear stress and Lu, Ly between for Newtonian fluid. It is a straight line. Yeah? Okay, Newtonian fluid is a straight line. For non-Newtonian fluid, we can go this way or we can go that way. So this is Newtonian. This is non-Newtonian. Okay, same also. So for non-Newtonian fluid, the relationship between shear stress and the velocity gradient or the shear strain rate is non-linear. Okay, non-linear for non-Newtonian fluid. Okay, so that is for part question 1, part A and B. C already done in lecture, so we skip C. Yeah? Okay, let's go to question 2. Question 2. Does it look familiar to you? Yeah? Does it look familiar, this diagram? That is if you attended my lecture. Oh. Exactly the same, is it? Okay, this question 2, last year's exam paper. You familiar or not? If you answered, and your friends sign attendance for you. I remind you attendance. Okay, this is found in lecture slide 102. Look at lecture slide 102. Is it there? Review 102. Okay. Look at that. This is lecture slide 102. Is it the same? Everything the same? Same, It is different, only numbers change. So, do all your tutorials and get and all of my lectures. Okay, so question 2. Question 2. B, we skip. This is B. Question 2, B. Okay, question 2B, we skip. Okay, this is B. Alright, we skip. We do A. Question 2A. A. Okay, what does A says? State with necessary mathematical representation the 3 important principles governing a parallel pipe flow system. A parallel pipe flow system. Alright, can anybody tell us what are 3 important principles governing a pipe flow system? What is the first important principle? Anybody? What's the first principle? Anybody? Q2, Q2A. This is August 2014. Where's principle number 1? Anybody? Principle number 1? Huh? Take on the balance. Heat loss balance. I see, I have to take off the balance. Okay, this is one of them. Okay. Okay. So if you have, for example, that particular question there, and let's say that, let's go 1, 2, and 3. Let's 2 and 3 here. Okay. 1 is actually the total flow. Okay, total flow entering. Throw away 4 actually. Total flow entering each joint. Okay. Must what? Must equal total flow leaving that joint. Okay. It's actually what? Conservation of mass. Okay. This is actually this mass conservation principle. Mass conservation principle. Okay. Fluid going into a system, a network, must equal to the fluid leaving. Okay. So we have for joint, for example, for joint B, what do we have? Flow from AB must equal to the flow rate through joint BCE plus flow rate through joint B to the branch BDE. Okay. Then for joint E, we have flow rate through branch BCE plus flow through joint BDE must equal to the flow passing through the pipe EF. Okay. And then at the end, eventually we must have flow going through the section AB must equal to flow leaving or flowing through the pipe section EF. Okay. Alright, so there's mass conservation. The other one, as one of your friends said, the head loss. Head loss between the two joints, E and E, is the same. It's the same. Okay? 2 is the head loss between joints B and E. B and E is the same. It's the same. So in other words, we have head loss represented by H, subscript L. Head loss through the branch of the network BCE is equal to the head loss to the branch of the network BDE. Okay? BCE, BDE. Okay. And the third principle is what? What's the third principle? Anybody can tell us? Okay, proportion, Proportion. Proportion. Okay, that is good. So proportion of total flow passing through each branch will be constant. So what does that mean? What does that mean? That means, right here. I don't think the right answer is there. Okay, let me just explain here. Just to example. So in other words, this is the pipe. Okay, this is your piping network, and you have A, B, C, E, F. This is D. This is A, B, C, D, F. Okay. So in other words, example. If the flow along AB, let's say in the first instance, this is 10 meter cube per second. Okay, going into AB. And let's say, for this case here, under 1, 40% goes through BCE. So this will be 4 meter cube per second. Okay, and therefore, for the branch BDE, it will be 6 meter cube per second. So there's a 40-60%, 40-60 or 4-6 proportion. Now, for example, for example, if the flow along AB has increased to 20 meter cube per second, so the flow through BCE, in this case, will be how many meter cube per second? And then through BDE, will be how many meter cube per second? If the flow through AB now increased to 20. So here will be 8. Okay, here will be 8. And here will be 12. Okay? That's what it means here. Alright? Right? Proportion of total flow passing through each branch will be constant. Right? Okay, so this is question 2 part A. So question 2 part B is that we have already covered in the lecture. So question 2 is done. Done. Okay, question 3. Can I go to question 3 now? Can I? Question 3, after question 3, we take a break. 3 is August. 3 August 2014. Okay. Okay, question 3. Let's look at question 3. See what it says. Have we come across this question before? Tutorials or in the video lecture? Yes or no? Huh? No. No, then we do it. No. If yes, then we just go on to the next question. Okay, describe with necessary graphical representations all the possible mechanisms of fluid motion and kinematics. Okay. That's part A. And B is the velocity field of a two-dimensional flow is given by that vector equation. B is to xi minus yj. Okay. Then D has got several parts, 4 parts. First is using this, obtain an equation for the streamlines of the flow. Second part is sketch some streamlines on an xy plane, taking both positive and negative domains for the x-axis. Third, derive expression for the stream function and use the flow field. And finally, the particle is initially means what? That's it. Is the word initially important or not? If a free particle is initially located at x equal to 2, using the pathline equation, show that the location of this particle with time can be traced from x equals to 2 to the power 2 times e to the power t. So part 4 here, part 4, any significance on the word initially is located at x equal to 2. Is it important? That's why when you look at exam questions, sometimes there are some hints given to you, some information. It may be hidden to those who don't know, but to those who know, it's actually an important information. So what do you think? Initially located at T and X. What is this for? What do you think? Initially means what? T times T equal to 0. At time T equals 0, X is located, X is 2. The particle is at X equal to 2. So how can you use this information? What is this for? This is actually one of the boundary conditions. So what are boundary conditions for? For you to find what? Later on, as you do integration, you get arbitrary constants. Okay, so boundary conditions are for you to determine your arbitrary constants. Okay? Alright? Alright, let's do first part so then we take a short break. Okay, first part is descriptive. Okay, this descriptive part actually is your notes. Okay? Just put there A. This is actually your notes actually. You look at, go back to your slide 69 to 71. Slide 69 to 71. 69 to 71. That is the answer. That's the answer. Okay? There are a few slides. This is 69. 69, 70, 71. That's your answer to part A. Okay? See, there are four. See, there are four possible ways which the fluid can move. Okay? And of course, one is translation. It means looking straight linear motion. The straight linear motion. It's not Tai Chi, straight linear motion. Okay, this is what it means here. Translation. Can go this way, and go this way, this translation. Then next is of course rotation. Okay? Rotation. Then you can rotate. Rotation, not rotate. Alright? Then you have linear transformation. If it is stretched, of course, then you move inner, but you will extend along this way. Okay? And if it's stretched this way, then of course it will reduce in its dimension and it will extend in the vertical direction. Alright? Then there's linear transformation and linearly. Then of course there's the angular deformation. Previously it was linear, now it's angular. So it actually is being, because of shear forces, a rectangular particle like this can actually be sheared and become the dotted shape. It becomes dotted shape. Right? So that is your answer to part A. Part A. So I don't have to write it down. Okay. Alright, so that's part A. Answer found in slides 69 to 71. Okay? Right. Then next is B part. B part. So far so good? Is it okay? Alright or not? Alright, huh? Good enough. No response. covering what has been covered before. No point. You know, all very intelligent people, no point doing things twice. Right? Do things once enough already. Eh? You don't have a time. I say you're very intelligent people. You don't have a time. Okay. So we have. We will go back to the question again. Okay, given this block, this vector equation, obtain equation for the streamline of the flow. So how does the equation of a streamline look like? Can anybody give a rough indication? The equation of a streamline, how does it look like? In what form? Anybody? The equation of a streamline actually involves an equation that has x and y in there. It's like elementary mathematics. One equation has x and y. You know, these two variables in there, and also probably with a constant c. And c is an arbitrary constant. C can take any value. So if you put c equal to 1, for example, for example, your xy equal to c, a simple streamline equation. X times y equal to c, yeah? Okay? So if you put c equal to 1, then you can plot a straight line already of x versus y. So you get one straight line, whatever direction it goes straight or that way, for c equal to 1. Then if let c equal to 2, you can plot again another line, whether this way or that way. Okay? Next to it, the first line. So you have the second straight line. And let c equal to 3, and you can plot again and so on and so forth. So c gives you a family of straight lines. Okay? Alright? Alright, so let's start. We are given this vector equation. V is equals to x I minus y j. Okay, you know I and j, they are unique vectors okay, in the x and y direction. So, what is the velocity? In this case, what's the value of u? U equal to what? In this case, equal to x, and therefore y equal to v equal to minus y. This is d. Okay, d equal to minus y. Okay. With u equal to x and v equal to minus y, can we develop the equation further? We also know that dy dx is equal to what? dy dx is equal to d over u. Absolutely. So therefore, dy dx d over u. What is d? d is minus y and u is x. So d is minus y and u is x. Okay? And then so what next? You can rearrange. You can say therefore IE dy. Let's put this. Okay, dx. Put dx here. Dx over x is equals to minus dy over y. Okay, dx over x equals minus dy over y. Okay, and what else can we do? We can integrate. Okay, we can integrate. Right? So when you integrate this, what do you get? You get log x on the left hand side equals minus log y, and you can put c or plus c. So we just put log c because c is arbitrary. You can put b and b equals log c. Also can. So it's arbitrary. So we can put log c, right? And just rearranging it. If you have just rearranged, you would get log xy is equals to log c. Okay? So therefore, xy is equals to c. And that is the equation of the streamline. Okay? Equation of the streamline. And this one looks very familiar to you, right? xy equal to c. Looks very familiar. You know the spray jet? spray jet example in your lecture. XY equal to C, you come across that streamline equation. So it looks like a spray jet. Yes or no? Spray jet. Very good, right? It's somewhere there. So you look at go back to your spray jet slide. Okay? You get this same streamline. So if you were to sketch them out, you get spray jet. Spray jet. I do a rough sketch for you, right? Okay, put like that. So, we got a question again. Question says, okay, so we got equation or streamline, that's part 1. Okay, so part 2, part 2 is to sketch. Okay, sketch some streamlines on an XY plane, both positive and negative domains for them. So, we need to do some sketching. So, we do sketching. We look at the spray jet. Okay, what's the spray jet? What's slide? Oh yeah, okay, by the way, it will look something like this, Okay, so this is your X and this is your Y, This is, for example, 0, and it can be 0.1, 0.2, 0.3, 0.4, 0.5, minus 0.1, minus 0.5, okay? And you can go right up to 200, 400, and even 600, up to you. So, if you were to plot the streamline, using the streamline relation, x times y is equal to c, you should be able to get streamlines like this. Okay? And this could be, for example, a certain value of c. Okay? So you will get a series, this is different color. You see it? You see it? These are for different values of c. Okay? You get. And so on and so forth. And similarly here as well. Okay, another one. And so on and so forth. Okay? So it's like a spray jet. Spray jet. Alright? Like you already see. Because for spray jet, you get the streamline, same streamline as your xy is equal to c. So, in other words, for example, this one at this point here, at this point, when x equals 0.1, y is equals to maybe 30. Okay? And this could be, for example, for c is equals to 2.5. Example here. And then you have another point here all the way up, x1 all the way up this one. When x is 0 point something, y is 0 point something. Okay? This is for c equal to, example, 5. Okay? And then you have another one, example again. Okay? When x is 0.1, y is 200. Example is for c equals to, let's say, 10. Okay? So you give your own values for x and y and do a sketch. Is that clear? So that would be part that's to sketch some streamlines on the xy plane. Okay, on the xy plane. So both positive and negative domains. Okay? And part 3 is derive expression for the streamline that use the flow field. Okay? derived expression for the string function, sorry, this derived expression for the string function that use the flow view string function. You want to take a break first? 5-minute break. Okay, toilet break. Okay, please go ahead. Take 5 minutes at 12, 10.